Hey guys, here's our next lesson, 7-4 arc length. We're not going to find the surface of revolutions. This is what would be used if we were going to do that. I'm going to save that for the Calc 2 teachers. But 7-4 finding arc length, we could do this if f is smooth and a continuous differentiable function on an interval a, b, a closed interval. So let's take a look and see what that would look like. Here we have our closed interval from a to b. And we have our curve. We'll just use this one as an example. We've seen curves like this before. If we wanted to find the arc length here, what we can do is we could actually use this formula where S represents the arc length of the integral from a to b, finding the square root of 1 plus the derivative squared with respect to x. Of course, f prime is the same as dy dx, so we're going to show you where that comes from, but here's the picture that would be associated with it. We can think of this as going from here to here, this increment, where this would be the change in x, the horizontal distance, the change in y would be the vertical distance, and this would be our first partition there, and that would give us an estimate here, as we can see, of that actual curve. And we can continue to do this along this curve, finding delta x and delta y, and then adding those up to get an idea of what the approximate length of this curve would be. Okay, so here's the proof here. Of course, since this is AP, I'm going to work through this with you. I think it's going to have way more lasting value if we do that than if I just were to give it to you. But sure enough, if you guys just know this formula here, that would be enough for you to be able to find the arc length, okay? But we can see here this arc length can be approximated by using the distance formula, squaring the change in x, adding it to the change of y squared, and taking the square root. That would give us, referring to our diagram here, one of these portions. If we were to do that multiple times and add them up, it would give us an approximation. Okay, this would be taking the summation of all those using summation notation, which we've seen. So all of this up above can be represented simply by the summation notation sigma. Once we have that, that statement there, what we're going to do is we're going to actually simplify that by using this idea of multiplying by a form of 1. So we have delta x over the square root of delta x squared, which is delta x divided by itself. This is a form of 1, and we've talked a lot about that this year. But if we were to take that and actually run the limit of that as n goes to infinity, we end up with the formula that we have up above. So I'm not going to spend too much time, but I think that's a pretty good explanation of where it comes from. It uses this limit idea of taking an infinite number of segments as we run as delta x and delta y run to 0, okay, because there's going to be an infinite number, we get the true length of this arc. Okay, and that's what we're going to be using here to actually find the arc length of the curve of a parabola that is reflected over the x-axis, which would be raised 9 units. Okay, the x-intercept there, if we set that equals to 0, would be 3 and negative 3. But we are going to keep it, as it says here, with this restriction just to the positive x-axis. So up here, we would be at 9, because that's where the vertex would be, and it would be opening and crossing the x-axis as we just mentioned here. So we're going to find the arc length of this arc by applying this formula right here, and I'll use the notation dy dx. So we have our function here, and I'm going to first find dy dx by finding the derivative of that function, okay, which would be negative 2x, and then I'm going to square that dy dx, which would be negative 2x squared, which would be 4x squared. And then what we're going to do with that is we're going to plug that into the formula. S equals the integral. We're running this in terms of with respect to x, so everything is in terms of x. So it would be from 0 to 3 along the x-axis that we want to run this. And it's going to be the square root of 1 plus 4x squared dx. Now we run into an issue here. Obviously we want to integrate this function. It's a square root function. If I were to make the composite function u 1 plus 4x squared and find the derivative of that, there would be no way of fudging and fixing or getting around the fact that our derivative would have a variable in it. So this would be one that we would have to use the calculator. We would go into the calculator to get an idea. We would plug it in and we would say that we would see that this is approximately 9.747 units long. Units just because it's a length, okay, not cubed or squared as though it was a volume or an area. Now what's kind of cool about this, guys, I'm going to show you this. If we were to go back to this diagram and I actually draw a straight line from 9 to 3, this would create a right triangle. And just to give you an idea of how close we can get without using calculus, now of course calculus is the way to go because it's much more accurate, we could just set up and use the Pythagorean theorem. Okay, so if we use the Pythag theorem, we would see that a squared plus b squared equals c squared. So we'd have 3 squared plus 9 squared equals c squared. C squared would equal 90. And then c would be the square root of 90, which is approximately, in your calculator, 9.487 units. Excuse me. There we go. All right, you can see without calc, we can get pretty darn close to the length of this curve. The length of that hypotenuse would be 9.487 units. The actual length of the curve would be 9.747 units. And this is off just because we needed around it. This is very close to the actual length of that curve. Okay, so it's pretty cool, as we've done before in most of our studies here. We have found stuff in terms of x, and we have found stuff in terms of y. So on the next page here, we're talking about everything in terms of y. Okay, so we could see the formula is the same. They just like to use on the interval from c to d, so it differentiates between things with respect to x versus y. And we're going to actually integrate this with the derivative of x with respect to y, all in terms of y. Okay, so this would be perfect for a function that would say x equals, and that's what we see here. Okay, I'm not going to get a picture of this guy. I just want to find the arc length of this curve, and we're going to find it from 1 to 3. So the first thing we're going to do is we're going to set up our function here. And now I'm going to find the derivative of this guy, dx dy, which is going to be, we bring this down, we multiply, we take 1 away. And now I'm going to actually square that guy. So if I square dx dy, because the formula tells me to do that, we get 2 squared 4, y to the 1/2 squared is y, so we get 4y. So now I'm ready to use our arc length formula. I'm going to integrate this guy all with respect to y from 1 to 3. And it's the square root of 1 plus dx dy squared. And now this is one where we can actually integrate by hand. This one we would make u equal to 1 plus 4y, so du would be 4 dy. You could see here we're missing a 4, so I'm going to fudge with the 4, and I'm going to fix it with the 1/4. And now we're ready to rock and roll. We're ready to work this through. Think of this as being raised to the 1/2. So when I add 1, I get 3/2. I multiply by the reciprocal 2/3. And that gives me, let's see, 1/6 times 1 plus 4y to the 3/2, and I want to run that from 1 to 3. So keep in mind it's the upper bound. We're going to plug in the upper bound, and I get the square root of 13 cubed minus the lower bound, the square root of 5 cubed. We can clean this up a little bit more by distributing the 1/6. We can pull out a 13, pull out a 5 here. So I get 13 root 13 minus 5 root 5 all over 6. That would be the exact value, the exact distance of that length, that arc from 1 to 3 on the graph. Okay, so the only difference there is two things. One, this was with respect to y. First one was respect to x. This one we were able to find exact value without using the calculator because we could do it by hand. Okay, so just have to be able to know those scenarios and how to handle those. Okay, we're going to look at one that gets a little bit more interesting because of the math that's behind it, and that is number 5 here. Okay. And again, if I'm going too quickly, you can always pause the video. You can always rewind, watch again, and I think you guys will be okay. You're going to see one like this on your homework. There's a homework problem that deals with this. You'll see it creates a special scenario, but the concept doesn't change. We're going to find the arc length of this arc between 1/2 and 2. So I'm going to first find dy dx. Okay, which is 1/2 x squared minus 1 over 2x squared. I'm then going to square that guy, because that's what we need for our formula. And just be careful, I'm squaring a binomial here. It looks a little fancy, but it's not too bad, okay? What we get is we get the first squared. The first squared will give us 1/4 x to the 4th. I get the first times the second. So the x squareds would cancel. I would flip and multiply, and then I would multiply that by 2, and that would give me negative 1/2. And then it's the second squared, so it's plus 1 over 4x to the 4th. So this is dy dx squared. So now I'm going to plug that into the variable. Plug that into the formula. S equals, we're going to integrate from 1/2 to 2. It's the square root of 1 plus all this stuff. Now watch what happens here. This is pretty cool for you math fans out there. Okay, when we do that, we get 1/2 here. 1 plus a negative 1/2 is 1/2. And what that creates in our algebra world is 1/4 x squared plus 1/2 plus 1 over 4x squared. It creates a perfect square trinomial. Sorry about that camera work. I'm gonna have to fire my cameraman. So this is a PST, which means if this is a perfect square trinomial, that could be factored, which it can be, which is kind of cool. So this can be factored into the quantity 1/2 x squared plus 1/2 x to the negative 2. Now I could have kept that down below if I wanted to. Okay, squared. So now this square and the square root cancel, and I'm left with the integral of 1/2 x squared plus 1/2 x to the negative 2 dx. And now we can integrate, evaluate, and to save time, we would do this by hand, because we can. We would get 33 over 16 units, okay? So again, this creates a perfect square trinomial. Just as a little bit of a review, a perfect square trinomial is where the first is a perfect squared, the last is a perfect squared, okay? The first times the second times 2 would give you that middle term. So if I multiply this times 2, so it'd be 1/4 times 2 is 1/2. This is a PST. Okay, so that's a unique situation that you will see in your homework. Just keep an eye out for it. Okay. Yeah, so this should be, you guys should be okay with this. You should be on your way with the homework, and I will check back in with you guys when we integrate by parts, our final lesson of the school year. Okay, so I'll see you guys soon. Take care. Hope everybody's doing well. Bye-bye.